on the recording right now. I'm assuming you can all see the screen, so it should show systems of nonlinear equations, correct? Correct.
Yes.
Yes. Whoa, that was loud. Okay. Okay, I'm gonna open up the chat just in case someone wants to ask something. So let me see. Oh, I got 25 participants. Let me see if I can. Okay, so not all of you have video. I can see at least 5 who have video. Do you see each other? Hi, Emily. Do you see each other on this video thing? Okay, great.
Yeah.
Okay, I hope you're all doing okay, and let's go ahead and get started. So I'm assuming just a few things out of the way. I'm hoping that you all got to read the announcements that I've been sending out, and they're important regarding exam 2, what's going to happen with exam 2. And the idea is going to be, the entire exam is going to be administered on Canvas. You will have multiple choice questions and numeric answer questions. Each question is going to require handwritten work, okay? But then you'll get to choose the answer. But after the exam is over, you'll go ahead and take and answer another assignment or quiz that only has one question that has a file upload in it. So after you finish the exam, you go either scan or take photos of your work, put them into a PDF, and then upload. Okay. So if you have any issues with that, let me know. But I'll probably give you about 12 hours or 6 hours to get your work scanned and put up, or just open it for 24 hours if you want to scan it. And try to print out the sheet that I sent to you that has unit and name on the top. Print as many of those as you like, okay? And I'm hoping all of that is clear to you. You have a quiz today. We're going to do a lot more quizzes now that we're online. So these are going to be low stakes because everyone is, you know, away and secluded, etc. So we're going to do a lot of low stakes tests from now on. Okay. Now, the purpose of this lecture is to finish off with nonlinear solvers. I'm hoping that you went through the first set of lectures. Can you send that printing sheet? The sheet has been printed, has been sent out. Sovit, it is on Canvas. Please follow my announcements and you'll be able to get a link to that and you can download it. Thank you. So so the first set of lectures for nonlinear solvers dealt with a single nonlinear equation that had a single unknown that showed up nonlinearly. Today, we're going to extend our knowledge to systems of nonlinear equations. So these are 2 or more equations that are coupled nonlinearly, okay? So I'll start with an example. Okay. Let's start with an example. So consider these 2 equations, 1 over 2x cubed plus y equal 4x, and y equals sine x ex, okay? And say you want to plot these 2. The one in black is the first equation, and the one in red is the second equation. You're plotting y versus x, okay? So now my first activity to you, and I'm going to try to put you in breakout rooms. So I got, what, 31 participants. Maybe we'll randomly assign 3 breakout rooms, okay? So the first activity is going to be, what does it mean to solve a system of equations, specifically nonlinear equations? So if you remember the first, when we had a single equation, we said solving a nonlinear equation was equivalent to finding the roots or the points where that equation intersected with the x-axis. Okay, so now my question to you is, what does this mean for, what's the equivalent of that statement for 2 equations? Let me break you into breakout rooms, assign 30 participants into 10 rooms. Okay, or maybe, yeah, 10 rooms, okay? So automatically create the breakout rooms and open all rooms. So I opened all rooms. So you've all broken out into rooms, but I don't know what happened to my slides. Okay, these are my slides. Okay. So your timer has started. I'm hoping you're still listening to me. You got 1 minute. Please join your breakout rooms to answer this activity. What does it mean to solve a system of equations, or specifically in this case, a system of nonlinear equations? To remind you, when we dealt with a single nonlinear equation, solving that equation meant finding the points at which the curve that represents that equation intersected with the x-axis. What does it mean for the case of 2 or more equations? Okay, you got about 10 more seconds. Okay, stop, it's time. All right, so let's see if I can see any participants from the rooms. Can you talk to me? Can someone just say something from one of the breakout rooms, because I don't see you. I don't see the breakout rooms. Hello? Okay, so let me close all rooms. All breakout rooms will close in, okay, 56 seconds. All right, should have accounted for that. Okay, so for those who are just joining, everyone is in a breakout room doing the activities. And this first activity was to answer the question, what does it mean to solve a system of nonlinear equations? So if you remember, with a single equation, what we meant was that the curve, finding the points where the curve intersected with the x-axis. Now, what does it mean to solve 2 or more equations graphically and visually? And what you're seeing here are the 2 equations to your left, to the left of the graph. Okay, so the breakout rooms apparently need 60 seconds to close. I did not know that. So essentially, you had 2 minutes to find an answer. And I don't see all of you over here, so I'm gonna randomly just select someone. Let's see. Paige, do you have an answer for us? Do you want to unmute?
Yes, when the 2 equations intersect.
Intersect what?
Is when you solve the system of equations.
Okay, but they intersect what? Each other or the x-axis? Each other. Okay. Okay, so in other words, what Paige is saying, that's the correct answer. So in other words, what we mean when we say we're solving a system of equations, whether linear or non-linear in reality, is that we find the points where all the curves intersect with each other. Now, what I'm showing here is, I mean, you could only do this in 2D or maybe 3D. When you get more equations with more unknowns, it becomes hard to visualize. But in essence, in any dimensions, what it means is to finding those points. I'm going to try to annotate. Do you see my cursor over here? So let me try to see if I can annotate. So what we're talking about is finding those points where where the curves intersect with each other. Okay, so obviously, just like with a single nonlinear equation, you could have one or more roots. Okay. Now, unlike what we did with a single equation, where we looked at the bisection method and the secant method and the regula falsi method, we're gonna just go after the most sophisticated method, which is Newton's method for systems of nonlinear equations. So we're gonna do this next. Okay, let me clear the annotations, clear the drawings. Okay. So the first step in Newton's method, if you remember, was to write the equation in residual form, okay? So now that we have these 2 working equations, I want you to take a minute and try to write those in residual form. Let's see, did you like the breakout rooms, or was it strange? No, you didn't like the breakout rooms. Okay, do these activities individually now. Show me that you grabbed a piece of paper or your iPad, okay? While I enjoy the nice beach over here. Oh, I see Eric is also in Hawaii, I suppose, or Florida. Okay, so you got a minute. Paige was all alone. Sorry, Paige. So if you're sitting next to someone, like I know Paige and Katrina, they're sitting they're in the same room. So yeah, work together. Great, I can see you. Okay. So yeah, feel free to work together. Yeah, you got about 10 more seconds. So the question was to write these equations in residual form. And again, the residual form was to standardize the solution method. Rather than saying we're going to intersect the curve with another value, we just want to intersect the curve with the x-axis, for example. Okay. All right. So let's see time. Okay. I'm going to randomly select someone. All right. Andy, are you here? You want to unmute?
Yeah.
Yeah. So do you have an answer for the residual form of these equations?
I didn't get to an exact answer. I was trying to think about what would be considered like alpha in this instance.
Okay. Do we have any other answers? So I know what you're saying, but there's no alpha in this case. It's just we want to cast the equations into a form that's in residual form. So Brendan Postma, go. Unmute.
So I got y equals 4x minus 1/3 x to the third minus sine of x.
Okay, so that's not the residual form. What you did, you combined these two equations into a single nonlinear equation, which is what you should do if you can. So this example kind of allows you to do that. But what if you had square root of y, or like, you know, log y at the bottom, right? Or something, or exponential y, where you could not set, where, these are bad examples. Let's say y cubed equals sine x e to the x. You couldn't, and upstairs you had also y to the fourth, for example. So then you couldn't separate, you couldn't combine those. So we're not trying to do a trick to simplify the system. We want the residual form for a system of equations. Okay, any other takers? I have one more choice. Okay, Eric. Yeah.
So does the residual form just mean to make to put everything on one side so that it all equals 0?
Yes, yes.
1/2 x to the third plus y minus 4x equals 0.
Uh-huh, uh-huh.
And e to the x minus y.
Yes. Okay. So Eric has the answer, but I'm going to generalize Eric's answer, and rather than just write them as equal to 0, I'm just going to define this as a function, because that still is a function in and of itself that can take multiple values. One of those values is 0. Okay. So instead of what Eric suggested, I'm going to define a new residual function for the first equation. I'm going to call it F1. You could call it R1 for residual, and then move everything to one side. And same thing for the second equation. I'm going to move everything to one side. Doesn't matter what comes before the other, whether you do sine x ex minus y or y minus sine x ex. It doesn't matter, because once we drive this to the root, that sign is not going to make any difference. Okay. So this would be the residual form. And now the meaning of solving this system now means finding x and y such that both f1 and f2 are equal to 0 at the same time. Okay. In the previous interpretation, we had to find x and y such as both equation 1 and equation 2 are equal to each other. Okay. Whereas over here, they're both equal to 0 and equal to each other, but they're both equal to 0. That simplifies our analysis significantly. Okay. So the next step in Newton's method was to write the Taylor series of the residual function. However, now we have our residual functions. They are multidimensional, right? So we have two unknowns in each of the residual function, correct? So therefore, we need the version of Newton's method that applies for multidimensional functions with multiple variables. Okay. So previously we had only a function with a single unknown, x, we called it. Now we have x and y, two unknowns. So we need the version of Newton's method for multiple variables, and that's given by this form. Again, think of Taylor's series as trying to predict what the function looks like around a point. And that point we're going to call over here x0, y0, and then you expand the function around this point using its derivatives. However, now we have derivatives in the x and in the y direction, or derivatives with respect to each and every unknown in the function. So if you have a function f of xy, the Taylor series will look as the function evaluated at the point that you know, x0, or you start with x0, y0. And then you start expanding in each direction. In the x direction, you get x minus x0 df by dx. And in the y direction, you get y minus y0 plus df by dy. It gets more complicated with higher order terms, but we're not going to be interested in higher order terms because of the next step. But keep that in mind, okay? So that will be the general recipe. Now, your next step is to write the Taylor series for a system of nonlinear equations described by f1 and f2, okay? Around point x0, y0. Now, hint, hint, we're gonna take x0, y0 as our initial guess. So if you did the work for the Newton's method for a single variable, okay, the same thing applies here for these two variables. So just write the Taylor series for f1 and f2, okay? So essentially just substitute what I have for the Taylor series for f1 and f2 around x0 and y0, all right? You got about 1 minute. Okay, so I have a question from Paul asking me to display the functions. No, I don't want you to do it for those specific functions because that's just one example. I want you to do it in general because we want to derive the method in general. So just do it for f1 and f2, okay? Okay, actually it's time now. So I'm gonna randomly pick someone. Let's see. Salim, are you there? Salim, can you hear me? Okay, Salim is not responding. Let's see, Pietra. The tired triads. Are you there? Pietra. Okay, so it seems that I got a lot of bots, I suppose. Okay, let's see. Do I have any takers here? I have no takers. Okay.
Oh, I guess I could.
All right, Katrina, go ahead. Okay.
So okay, it would just be the same thing, but with like F1. A subscript was like F1 for the equation, and then F2 for the other equation.
Yep, exactly. Just change F1 and F2. That's all there is. However, you got to make sure what I missed here in the definition is that these derivatives are evaluated at x0 and y0. Okay. So now, depending on what F1 and F2 are, you just evaluate these derivatives, and because you know these residual functions, you should be able to evaluate those derivatives. Okay. So let's go next. What do we do next in Newton's method? So remember in Newton's method, what we did, we wrote the Taylor series, and then we truncated that Taylor series to the first two terms. So this was the Taylor series for a function with a single variable, and then carried out to second order and further, and then we truncated. We only took terms up to the first derivative, and then we set our residual function equal to f of x0, which was treated as our initial guess, plus x minus x0, f prime of x0. And then what did we do next? We said, okay, we want a recurrence formula, a recipe to update our initial guess x0. But we're looking for f of x equal to 0. So let's just set f of x equal to 0 on the left-hand side. So that gives you 0 is f of x0 plus x minus x0 f prime at x0. And then you simply solve for x. And that was Newton's method. And then we said, okay, this is our recipe to update the guess. We just start with x0. We calculate a new x. Then we make that x as our x0 and so on and so forth. And we had a general form, xk plus 1 is equal to xk minus f of xk over f prime of xk. Okay, so now our goal is to derive the two-dimensional version or the multi-dimensional version of this formula, all right? So if we do this, now, your next activity is I want you to try to apply the same strategy to the system of equations, okay? So take these two equations, F1 and F2, okay, truncate. So essentially just get rid of the plus sign over here. So keep these first terms. And I want you to come up with a recipe to calculate, to improve the guess X0 and Y0. So hint, hint, you're gonna get two equations, right? One for X and one for Y that are gonna have an update. But I want you to try to think, to try to relate this to what we did with the single equation for Newton's method. Okay, the same way we set f of x equals 0, over here, what are we setting? f1 and f2 equal to 0, right? So go ahead and try that. You got 3 minutes. This is going to be a long exercise. Hello, Connor and Abigail. I can see you. Good to have you. You should get a system of equations, okay? One equation for the update for X, one equation for the update of Y, okay? Or a coupled system of equations. We know how to deal with system of equations, all right? I'll give you another 30 seconds. Everyone. For some reason, I cannot see everyone. I suppose if you don't have a video, I cannot see you. Okay, try raising your hand. No, you can raise your hand with a, if you click on your control tab, there should be an option where you can raise your hand, I think. Yeah.
It's on the participants window.
Yeah, on the part, I cannot see that. Okay, yeah, I can see it. You can raise your hand. Let me see. Okay, well, okay, yes, yes, you all raise your hand. Okay, do you have questions? Or do you want to volunteer the answer? Okay, who wants to volunteer an answer? Because obviously I don't know who's, okay, yeah, I can see you, Katrina, I can see Garrett raising. Okay, Garrett, do you want to take a stab at this?
Sure. So my question was, so I did negative f of x naught y naught minus parentheses y minus y naught times by the partial differential of y divided by the partial differential of x.
Y, partial differential of y?
So df over dy.
Df over dy.
Yeah.
Okay.
That all divided by df over dx and then adding x naught to the end.
Okay, so think about what we're solving here, okay? We are trying to find x and y. Everything else is known, okay? So this is, if you can't see it, this is actually a system of linear equations. Okay, so the goal here is to write this in linear system form, okay? Do I have any other takers? Conrad, are you here? Do you have a suggestion? Okay. All right, so maybe I'll give you the answer. All right, so first we truncate the equation. So we remove this plus sign over here. So you agree that this is the form that's equivalent to the single equation, to the one with the single equation. Okay. Now when you look at this, x0, y0, f1, and f2 are known, and even df1 and dfx, df1 by dx and df1 by dy, and so on. Those are known quantities because you know f1 and f2, okay? And you know how to evaluate their derivatives at x0 and y0. So the only unknowns here are x and y. And in other words, this is nothing more than a system of a linear system of equations in x and y, okay? And specifically, specifically when you set f1 and f2 to 0, because that's what we're trying to solve, right? So if you do this, your first equation becomes this guy, and your second equation becomes that guy. Okay, so look what I'm going to do next. Okay, now I'm going to write this in matrix vector form. Okay, so I'm going to collect f1 and f2 into a single column vector. Okay, and then I'm going to collect these terms, df1 by dx, df1 by dy, df2 by dx, and df2 by dy. There's a pattern there, right? And if you look at the equations the way I'm presenting them here, they actually look like a matrix. And in fact, they can be written into a matrix form. Okay. You see this matrix form, df1 dx, df1 dy, and df2 dx, df2 dy, into x minus x0 and y minus y0 equal to 0. Now, I want you to visually verify that this actually gives you the system of equations written above the matrix vector form. So start with the first equation. You get f1. Can you see my cursor? Yeah. So you get f1, x naught, y naught. That's the first term over here. Okay, so maybe I get the annotator. What is the annotator? Okay, I'm going to draw. Okay, so I get this guy is this one over here. Okay. And then this thing over here, dotted with the column vector, gives you df1 by dx into x minus x naught. So it gives you this term, plus df1 by dy into y minus y naught. So it gives you this form, equal to 0, right? Same thing for the second equation. Okay, f2, it's not so hard when you see it now, right? f2 is this guy, and then df2 by dx, again at x naught, y naught equal x minus x0, and then df2 by dy into y minus y naught equal to 0. Anyone disagrees with this? So you agree that now also all of these quantities are known except for x and y. Now notice the interesting form how we wrote this here. We could have extracted x0, y0 outside, but we would have also to carry another matrix multiplication outside. So instead, we just combine them. We look for the change in how the root, the guess for the root we're interested in. We look for the change, x minus x0. And then once we know that change, we can compute the nominal value of the root, okay? So now I'm gonna take this one step further. If I can get to my screen, okay? So now, if we define x0 vector as the point x naught, y naught, okay, then we can call this entire vector a function, a vector of functions, right? So the same way you define a vector of values, you can define a vector of functions. But in fact, this is actually a vector of values where the values are the residual functions evaluated at x naught. Okay, so in other words, this capital boldface f is a vector of the residual functions evaluated at x0, y0. And now we're going to give this matrix a special name and a special symbol called J, which stands for the Jacobian matrix, okay, after Jacobi, you know, the Jacobi method. So the Jacobian matrix is actually a general matrix where you take a system of equations or a system of functions of n variables, and you differentiate those functions with respect to all possible variables, okay? The Jacobian contains in the first row, you can think of it either per row or per column. If you think of it per row, the first row contains the first function differentiated with respect to all existing variables. So in this case, because we only have two variables, x and y, we're gonna have two entries, df1 by dx and df1 by dy. The second row is going to contain the derivatives of the second function with respect to all variables. You get df2 by dx and df2 by dy. Now the Jacobian is general. So if you had 3 equations and 3 unknowns, the first row would contain the derivatives of the first 3 functions and 3 unknowns. The first row will contain the first derivatives of the first function with respect to all unknowns, second row derivative of the second function with respect to all unknowns, and so on and so forth. Okay? Now next, I'm gonna call this change x minus x naught and y minus y naught, I'm gonna call this delta. Just a symbol, okay? Because this measures the change in the guess for the root. This measures how much we are improved, by how much are we improving the root. Once you compute delta and you know x0, then you can find x and y, okay? And then if we write this in matrix form, vector matrix form, you get f at x naught plus j x at x naught times delta equals 0. And then you take f to the right-hand side, and we know how to solve systems of equations. This is ax equal b, right? This is matrix times unknown vector equal to a right-hand side. And from that, we can simply extract the root j inverse at x naught times f at x naught, right? So just think about this for a second. It seems like surreal that we started with this system of equations and then ended up with linear systems of equations. And that's why we studied linear systems early on in the semester, because everywhere you turn, your goal is to linearize things, because we know very well how to, we know how to deal with linear systems of equations. Okay, now this is the multidimensional version of Newton's method. If you can compare this with Newton's method, you can do this on your own later. The inverse of the Jacobian is equivalent to 1 over f prime. If you remember Newton's method, so let me actually, I should have done that earlier. Let me contrast this to Newton's method. Okay, so let me do this right here for you. Give me a second. So Newton's method can also, okay, so look at Newton's method for a single equation. Okay, we had x equal x0 minus f over f prime. Now take x0 to the left-hand side, you get x minus x0 equal minus f over f prime, correct? Okay, so x minus x0 is the equivalent of delta, right? Where delta now is x minus x0, y minus y0, and z minus yz0, however many unknowns you have, okay? Now, f at x0 is nothing more than fx0, right? So we still retain that form. The only difference is that in the single equation, we had 1 over f prime. Now, what is the equivalent of f prime in multi-dimensions? It's the Jacobian. You have to differentiate with respect to all variables. And because this is a matrix, we cannot do divide by a matrix. Instead, we do the inverse, right? So that's why you see this j inverse instead of 1 over j, right? So they're identical. Multidimensional Newton's method is nothing more than, will reduce to the Newton method for a single equation, okay? So now I have an algorithm. If you know, and I'll help you program it now in a second, we'll do it together. It's very easy. It's just you have to define things in terms of NumPy arrays when you program them. But for the general Newton's algorithm, if you are given, you will be given a vector of functions, of residual functions, that's f of x. You will be given, or you will choose an initial guess x naught, and you will know how to compute the j, because if you know the residual functions, you will know how to compute the j. Agreed? Okay, given those things, the next step would be to calculate your Jacobian at the initial guess, or at whatever value of the root you're at in this case, you're starting with the initial guess. And you also evaluate f of x, the residuals at that x0. Then you solve for delta by solving this equation. Delta is minus the inverse of the Jacobian times f at x0. And then you update the roots. How do you update the roots? Remember, delta was x minus x0 and y minus y0, etc. Now you know what delta is, and you know x0. You can extract x, y, and z, etc. And then you update your, those will be your new x naughts, okay? Those will be your new initial guesses, and then you repeat and repeat. Really, the way this should be written is that delta at k plus 1, the new values of the root, are equal J inverse at the previous value of the root times F at the previous value of the root. Okay, so now let's apply this to our example, and then we'll go ahead and program it together. So F1 was 1 over 2x cubed plus y minus 4x, and F2 was y minus sine x e to the minus x. The Jacobian is given in this form, df1 by dx, df1 by dy, df2 by dx, df2 by dy. I've had you do a lot of derivatives through the semester, so I'm not going to ask you to do one more. Just visually inspect this, or if you're uncertain, do it as a self-assigned homework. This would be the general form of the Jacobian. Now, what you're going to do when you program this, you will program the Jacobian in terms of x and y, because that Jacobian is going to change depending on the values of x and y, okay? So, but you program the Jacobian in general, as if it's just a set of functions, okay? Now, on the next slide, I have an example of, the animations are all messed up over here, but I have an example of how you do this by hand. It's kind of annoying to do it by hand, really, but so this is only amenable to programming, so you should always do this programmatically. But just to, to illustrate how you would tackle this, we're starting with an initial guess at -2 and -4. Then you calculate the Jacobian and the function values at x and at those values, x and y. You just simply plug in the values, calculate a number, and fill in the blanks and the matrix for the Jacobian. And in the function, the residual functions f1 and f2, just so happens that f1 is equal to 0. So we stumbled kind of, actually that's, there's a typo over here. I think there's a typo over here. Okay, and then you solve for, no, actually, no. So you have to have both f1 and f2 equal to 0. So although f1 equal to 0 here, f2 is not equal to 0. So that's not a root. Okay, so no errors over here. Okay, I fell victim to my own little trick. Anyway, so now you solve for delta by simply taking the inverse of the Jacobian and multiplying it by f, and then you repeat and repeat and repeat. Okay, now I want you to pull up, I put up a Jupyter notebook with gaps for you called Nonlinear Systems on your canvas. So why don't you pull that up, and then we can program this system of equations together, okay? Let me pull that up myself. List of participants. Katrina Lee, you still have Katrina Lee. You still have your hand raised. Lower hand. Garrett, I'm gonna lower your hand.
Yeah, I'll unraise my hand.
You must be really tired now. Okay.
Yeah, no, I've been working out that way, just raising my hand.
Okay, so nonlinear systems with gaps. Okay, and I'll guide you through this. A little bit. Let me see if we can actually. For some reason, I cannot drag it to the other screen. Okay. Can you see my screen? Clear all my drawings. Let's go back to the mouse. Okay, can you see my screen? Okay. Okay, so this is what you're seeing. This is the same system of equations that I presented in the slides, and you'll see a few question marks. So let's go through this together. Have a description. You can go through this description at your own pace, but I've imported the general boilerplate NumPy, and from NumPy I'm importing sine, cosine, pi, and exponential. And again, the matplotlib couple of tricks to get high quality vector graphics plots. And then I'm importing this thing that I'll discuss in a second or later. It's called fsolve. It's actually, we did discuss this when we solved a single equation. So I'm going to show you that this also applies to a system of equations. Okay, and it's really cool. You only have to give it the vector of functions, of residuals, and it will do magic behind the scenes. Okay, so now we cannot plot the residual functions. I mean, we could, but those are going to be like 3-dimensional, and they're going to be really hard to visualize. So really just this one unique example, because it's 2D, we can plot y versus x. And these are the two functions that I'm plotting over here. And we're looking for these roots, okay? Now, the way we're gonna go at this, let me see if I actually have a description of this in the slides. I'm gonna switch back to the slides for a second. And okay, so okay, so what I have here is a kind of a suggestion of how you would program this. Okay, you would program it the same way you program the residual functions and the derivatives for the 1D case. Okay, remember in the 1D case we had to define the residual function and also its derivative. Over here you do the same, but instead of returning a single value, you have to return either an array or a matrix. You will return an array for the function, okay? And if you look at this f, the definition over here, I'm defining f, and I'm assuming that f is gonna take a vector of guesses or a vector of values. So you could force it to take x0 and y0, for example, or assume that it's required that it will take a array or list of values, okay? So in this case, I'm assuming it's gonna take two values. I'm gonna call those xval. And inside the function, notice what I do. I untangle that xval because I'm assuming it's an array. And specifically in this case, it's an array with two values. And the first value is x. So I get x is xval0. I call that x. And y is equal to xval1. That's the second value. And that ordering is gonna matter in how you define the function. So if when you create a function, either document it by saying, hey, you know, the first value corresponds to the x variable and the second value corresponds to the y variable. First value corresponds to temperature, second value corresponds to pressure. Just be consistent with that. However you want to organize them, it doesn't matter. But as long as you tell people what they mean, okay? And then simply you define the function f1. Now remember, those are actual values. They're not unknown. So we're not defining a function over here, f1 and f2. We're actually defining specific values of f1 and f2 at the values given x and y, okay? So that's why I just write f1 equal, you know, 1 over 2x cubed plus y minus 4x. And then f2 is y minus sine x e to the minus x. And then I return, so this is a value and this is a value. In other words, these are the values of the residual functions at what has been given to us in xval. And I simply return those in an array. So that's my column vector, f1 and f2, okay? So you should agree that this, I hope that you agree that this vector contains the values of the residual functions evaluated at x0 and y0. In other words, this is nothing more than f at x0, okay? All right. Does anyone disagree? Okay, all right. Now, next, which is the harder part, in the one-dimensional case, we had just to define the derivative. That was one value. Suddenly, now we've exploded in the number of values. We have 4 values to define for 2 dimensions, right? For 3 dimensions, you're going to have 9 values because you're going to have 3 by 3. For 4 unknowns, you're going to have 16 because you're going to have a 4 by 4 matrix, okay? So for the Jacobian, you do the same thing. I'm going to take the Jacobian. It's going to be evaluated at a specific value for x and y. So I'm going to pass it xval, and then I untangle those. I call them x and y because I want to relate this to these functions f1 and f2. And then simply return an array, and notice how I nested the array in terms of rows. It's an array built on lists, just like we've defined arrays throughout the semester. We're back to linear systems, right? This is nothing more than a matrix. The first row is nothing more than this Jacobian over here, 1.5x squared minus 4, and then 1 for the second column. And the second row, first column is minus cosine e minus x, and then plus sine e to the minus x, and so on. Okay, so now let's go ahead and do this in our Python notebooks. Okay, so if I open up the notebook, for some reason it's not showing. Okay, let me move this to this screen. Okay, So now go ahead and start filling in the blanks for F and J over here, okay? You want to define F1. I know I just showed you those, but I hid the slides, okay? So go ahead and define F1 and F2. F1 and F2 are given to you in equation 3 over here. And I'll show you the Jacobian. Okay, I'll show you what the Jacobian looks like on my screen, okay? This is what the Jacobian looks like, okay? And I have the structure already set up for you for the Jacobian. Okay, so go ahead, take a minute, fill in the blanks. So again, to be clear, this vector valued function doesn't return functions. It returns just two values of these residual functions evaluated at x val. You could pass, if you want here, x0, y0. It's up to you. It doesn't matter, okay? Execute this. All right, so I'm assuming that you already have this. So for F1, what we have to do is y minus 4x plus 1 over 2x cubed. So I'm just going to put y minus 4 times x, and then plus 1/2 times x cubed, okay? And then for F2, we have y minus sine x, which I already defined, or you could do np dot sine, times exp of minus x, okay, that times the exponential, and then simply return F1 and F2. Now, same thing for the Jacobian here. Our Jacobian is 1.5 x squared minus 4 for the first entry, so we just put 1.5 times x squared minus 4, okay, and then for the second entry is 1, and then for the second row is minus cosine x times exp minus x plus sine of x times exp minus x, okay, and 1.0. Okay, now you should verify this. You could say, okay, my x val, my initial guess is simply a numpy array of x0, y0. Let's say 1 and 3, okay? And then we can simply call f at guess. It's going to give you two values. That's the residual. The first value is the first residual function evaluated at 1, 3. And the second value is the second residual function evaluated at 1, 3. We can also calculate the Jacobian, j at the guess, and it's going to give us 4 values, minus 2.5. That's, you know, the first entry here, second entry, and so on and so forth. Okay. Now, the next step, which I haven't asked you to fill in the blanks because it's a little bit it requires a little bit of work. So I'm going to go ahead and just share it with you, and we will discuss it together. And I'm going to hope now that you are comfortable enough to just raise your hand and ask questions, okay, as needed. It's unlikely we will have a homework on this. So this is more for your own developmental knowledge in program, okay? It's really not that hard. I know you know how to do this if you focus on it. Okay, so what does our Newton solver require? Just like the 1D case, in this case, we're gonna require the residual functions, or in other words, now we need an array or a vector of values of the residual functions. So that's gonna be f. We need the derivatives, or the Jacobian, right? So the Newton solver, what is it gonna do? It's gonna apply, it's gonna solve this guy over here. It's gonna do delta equal minus j inverse times f over and over again. Because that x0, we're not gonna do it only for x0. We're gonna keep iterating, right? We're gonna take x0 initially, we're gonna update that will become our new x0, and so on and so forth. So our Newton solver is gonna take f and j, is gonna take an initial guess. We can call this x guess. I called it x for lack of creativity, but this should be an x guess, okay? So X is nothing more than your initial guess, and a tolerance, okay? We want to know where we stop, when we want to stop, okay? You can pass a maximum number of iterations if you want. It's up to you. Again, these are functions. No one forces you to write a function in a certain way. You can design it however you like, okay? Now, the first thing I'm going to do is I'm going to take these the function value, right? So what I need for this Newton solver is to simply calculate this delta. In other words, take the inverse of the Jacobian and then multiply it by f at x0. So the first thing I want to do is evaluate f at x0, and I call this f value, okay? And f value is nothing more than my function f evaluated at x, or the initial guess, okay? Now, next, we need to define an error because we want to stop after a certain tolerance. Now, if you remember, for vector valued, for vectors, we have to define a norm for the error, right? Either the maximum value or an L2 norm or something. So this applies here because, you know, if you want to evaluate the function check, if we reach 0 for every value, then you have multiple values, right? So you need an aggregate number, like we discussed when we were doing iterative solvers, okay? Same thing applies here. We need to get a sense of whether the functions are 0 or not, right? So, and the great thing over here is that once the functions are 0, you know where to stop, right? That's your true error, right? Because your true answer is f of x equals 0, right? So all we have to do now is calculate the norm of this f value. F value, again, is a list of values. It's like this guy over here, f at guess, okay? Okay, so now we calculate this error norm, and then, or, you know, we can start with an error norm, or we can set a very high error, never mind this line, okay? Because we want to loop now, as long as our error is greater than the tolerance, keep iterating, okay? So next, we define an iteration counter, and iter equals 0. Again, same with what we did with the one-dimensional case. And now we start our loop. As long as the absolute value of our error is greater than the tolerance, and as long as the number of iterations is less than 100. So over here, I hard-coded the number of iterations. Do you need this? No. You could say, as long as your absolute error is greater than a tolerance, okay? Or you could say, as long as my number of iterations is less than maximum iterations if you passed a maximum number of iterations. But in general, when you're using these Newton's methods, this would be part of a very large code where you have to call Newton's method billions and billions of times. And what we typically do, we actually hard code the maximum number of iterations to like 5. Because there's so many approximations going on, I really don't care if I reach a very tight tolerance in my Newton solver. I just don't want to spend my entire simulation just doing the Newton solve, okay? So we typically hard code this to a few iterations, okay? As much as we care about. So over here, I hard coded to 100 iterations, but typically, you know, you could either pass maximum iterations or not. It's up to you. Okay, now within the iterative solver, I'm going to calculate the Jacobian value. So that's my j at x naught, okay? Simply call j at x. This is like this one, j at guess. So that gives me a j value. Now that j value is actually a matrix, okay? Now we simply compute delta by solving the system of equations. You can either invert j and multiply it by f of x, or just do np.linalgebra.solve and give it the matrix and the function value. If you remember, the linalgebra.solve takes a coefficient matrix and the right-hand side, okay? So over here, what I did, I used this form to solve for delta. So this is like ax equal b, okay? My right-hand side is minus f of x0, and my coefficient matrix is j of x0, okay? That's what I'm doing here, okay? Now I computed delta, okay? Next step, we're done, really, but we have to iterate, right? So that delta is going to give us the improvement on the guess, okay? That's going to give us the improvement on the guess. If our guess is x0, y0, etc., right? Or x0 vector, or x in this case, that's where we started, okay? Then all I have to do to get the new guess is add delta to it, right? That's the difference. That's the increment to my initial guess, okay? And I'm going to put it in the same value for x, okay? So that gives us the new updated value for the root, all right? So in other words, what I'm doing here, this would be the first iteration of just f and j, and then we compute delta, and then we improve our root, okay? But over here, I'm going to do it in a loop. Okay, so now I have a new value for the root. I'm going to go ahead and evaluate my function f again, okay, to see where we're at. If all the function values in f are 0, if all the residual functions are 0, then we would stop there. The iteration would stop. Otherwise, keep repeating. So I'll go ahead and evaluate the function again, and then now compute the error norm. Now, automatically, once you hit this line, once you hit the last line, the while loop is going to check, is my new error greater than the tolerance or not? If it is, exit the while loop. Otherwise, keep repeating. And you will see as you repeat, we're going to keep improving and improving our guess. Okay? Now, once we're done, okay, forget these lines for a moment. Once we are done, you return the new root, the number of iterations, and the error. Okay? And what I have over here is checking if no solution is found. So let's say you hit 100 iterations and your absolute error is still greater than the tolerance, then return a negative value for the number of iterations, indicating that no solution was found. Or throw an error, or print a statement, print no solution found with several exclamation marks. Okay? All right. So let's take this for a spin. All right. So let's try to find the root between -2 and -4. So if you look at the curve over here, there is a root between -2 and -4. It's over here, this guy up there. Okay. So it should be around, I don't know, so there's a root between -3.5 maybe and about 5. Okay. So let's try to find that root. And I've given you the skeleton of the solution. Okay, so what you need to do. Okay, so the tolerance, I want the tolerance 10 to the -8, and let's try to find the root between -2 and -4. So I want you to put in an initial guess that you think is good, and then call the Newton solver. Okay, so go ahead and try this. Give you a minute. So if I don't see you raise your hand, please unmute yourself and talk to me, because I don't always see the window, the participant window.
I have a question for this.
Yes, go ahead.
With just the one-dimensional Newton's method, it sometimes gets stuck in local minima. Would there be a situation like that?
Yes, absolutely.
Okay.
Yes, definitely. Yes, it's just harder to visualize, but yeah, definitely. You'll get stuck. Now, typically, Andy, the good thing is that, and everyone, is that these are very special cases where you can visualize the function, you can pinpoint a bracket, and you can find the root. But in many complex applications, like in computational fluid dynamics, you have no idea what the curves look like. They're really complicated. They're really n-dimensional. But you actually have an idea of where the root is. And in a time-stepping procedure, we just simply we know that the root is only going to be very close to previous values that we started with. And so you take your initial guess as the previous value and just keep moving forward, okay? Now, remember over here, this initial guess is not a bracket, okay? Don't confuse this with the bracket of the bisection method. This is a single initial guess for each unknown, okay? So if you want to find the root between -2 and -4, okay? So there's a root between, so there's a root over here, what did I say, between -2 and -4. So my initial guess is going to be, let me see. So let's take our initial guess to be actually, for x, we're going to take -2. And for y, we're going to take -4. We're going to see if we converge to this root at the top, okay? All right. To find the root, this is actually an incorrect statement. To find the root less than -2, -4. Okay, so I'm going to actually put -2 and -4 over here, and let's see what we get. For Newton solver, what do we want? We want to pass the, oops, I need to execute all my functions again. Okay. So for the Newton solver, what I need is f, which we defined earlier, j, and my initial guess, x guess, and a tolerance, and then we let it run, and then it found a root. Print, it took n iterations. So let's see, n iterations, or number of iterations is equal to n, and roots, and it's going to find 2 roots. Okay, and it found the 2 roots, one at -1.4 and -4.28. So let's see, -1. It actually found this root over here. Okay, it found this root over here at -1.4 and about -4.1, right? So it found this guy over here, this root. Okay, you can pick different values. So let's say we want to find this root over there. That's a really kind of hard root to find, but we can start at maybe x equal -3 and y equals 0, let's say. Okay, so if we want to go x as -3 and y equals 0, let's see if we find that root. Yeah, so we got -3.3 and 5.086. Okay, so we got the root -3.3 and about 5.86. Okay. And you can verify for yourselves that if you call now the residual functions at x, or these values, you know, let's call these roots, okay? I'll call these roots so don't get confused with x, okay? So if you call f at the roots, what should we get? James, do you have an idea?
I don't.
So we found the roots of the residual functions. So if you evaluate the residual functions at the roots, what do we get?
Where the line intersect with each other?
But because we, okay, yes, but what's the specific value of those residual functions? The reason, remember the reason we wrote things in residual form is because it kind of standardizes things. That intersection point is actually 0, okay? Now, if we evaluate the functions, these residual functions at the roots, we're going to be as close to 0 as possible, down to a tolerance of 10 to the -9. So we should expect the error or the values to be about 10 to the -9, and that's what we get. The function values at the roots, they're actually just equal to this tolerance, okay? Because that's as far as we converged this residual system, okay? So that's the reason we wrote things in residual form, is that the residual form at the roots is 0, or in our case, because we're doing this approximately, is as close to 0 as possible, actually equal to the tolerance that we set. And our tolerance was 10 to the -9, okay? Or yeah, whatever we got, it converts things to 10 to the -9. Okay, so now if you want to do this with Python, with built-in Python, you can use the function fsolve, okay, like we used in 1D. Now ask, if you press Shift Tab, you ask what fsolve takes. It can take actually a vector of functions, okay? It doesn't matter if it's a single function. It can take a vector of residual functions here in func and x0, your initial guess. So forget about all the other ones. But if you do this, all you have to do is call fsolve on our f. You don't even have to give it the Jacobian, okay? You don't even have to give it the Jacobian. And we'll talk about that in a second. And then, so if we try to call fsolve with the roots x guess that we started with, we get the similar roots. So our roots were -3.32 and 5.08. Python gave us -3.32 and 5.08, which is pretty great. Okay, so that tells you we are on the right track. Okay, so that's what's great about fsolve. You don't have to, implement your own Newton solver, and fsolve works for an arbitrary number of functions. Okay, arbitrary number of functions. Okay, so I'm not going to go through example 2. I'll let you work on that yourselves. Okay, but it follows a similar procedure, and I have it in the slides as well. Example 2, it's the intersection of a circle of radius 1, okay, with this curve y equal x cubed minus x plus 1. So you first write things in residual form, you set up the Jacobian, and then all I'm asking you here is to go ahead and program it, and then call your Newton solver and call your built-in fsolve, and that should give you, you have 2 roots over here, so you can try it out with either one of those roots. Okay. All right. So now we can go back to our slides because I have a really nice activity for you next. Okay. So now we considered nonlinear systems of equations. Now I'm going to consider a system of linear equations. And I'm going to ask you the following question. To use, first ask yourself, can I use Newton's method to solve a system of linear equations? If yes, if no, then that's your answer. Don't proceed any further. But if you think yes, I want you to go ahead and apply Newton's method for this system of equations, linear equations. And let me show you, again, remind you of Newton's method. I'm just going to copy the equations over here. What you have is, I'm going to copy the governing equations for the general Newton's method. And I want you to try to use x0 and y0 equal to 0 as initial guesses, okay? And apply Newton's method to the system of linear equations, okay? So first thing you do, you write in residual form. So get f1 and f2 and just simply substitute values over here and see if you can solve the system of linear equations. Okay, go ahead. You got 3 minutes. All right. I'm back. Let's see. Let's take a tally of who thinks we cannot use Newton's method for systems of linear equations. I cannot see all of you because most of you don't have video turned on, but let's see. Do you want to either raise your hand or chat or open your microphone? Sovit. Okay, so I got it. Okay, so Paul thinks we can use, I think we can apply it from Garrett. Okay, Katrina, yes, yes. So I got a bunch of yeses. Yes, should work. Okay, okay, great. Okay, okay, I got it. I think everyone agrees. I got a full flood of chat. Okay, I got it. You're right. Yes, you know, there's nothing so special about actually linear equations are a special case of nonlinear equations, right? So in principle, yes, we should be able to apply Newton's method. And what I want to show you here is actually that you recover the solution of linear systems. So who was able to get to an answer? Okay, Brendan, do you want to talk to us a little bit?
So I got, because the Jacobi is just a matrix
Jacobian.
of values.
Yeah.
Oh, Jacobian, yeah, sorry. So it's Jacobi's 5, -1, 1, 4.
Okay, it's just fixed values, correct.
Yep. And then F is -2 and -3.
Right, so the Jacobian doesn't depend on the roots anymore, right? Because it's linear. You differentiate a linear term, you're just going to get a constant. So the Jacobian is independent of the roots. And then for F1, F2, X0, Y0, what do you get?
Oh, so I didn't get that far.
Okay, you didn't get that far. Okay,
it,
who got further than Brendan? So you only calculated the Jacobian. And then, do I have any takers? Emily, did you get anywhere?
I only got to the two matrices, and then I just need to calculate the inverse and then multiply the two together. That's how far I got.
Okay, that's quite far. All right, so I don't see everyone. Connor, do you have, Abigail and Connor, do you guys have an answer? No answer.
Well, so I guess after calculating out that matrice, you should get an answer of like 0.52 and
yeah. So okay, yeah, yes. So I don't mean to interrupt you, but I'm not actually looking for the specific answer. What I want to show you here is that Newton's method is nothing more than it gives you the basic solution of a linear system of equations. Okay, so let's go ahead and do it together. So we first define the residual functions f1 and f2. We take everything to one side. So let's just move the x1 and x2 to the right-hand side. So you get f1 is 2 minus 5x1 plus x2 and 3 minus x1 plus minus 4x2. And I'm sure most of you got there. Okay. Then the next step is we define the Jacobian. And like Brendan said, the Jacobian is constant in this case. It doesn't depend on the roots. So in other words, there's really like no iteration that can happen because the Jacobian is independent of the roots. The only thing that depends on the roots are going to be delta and f1 and f2. Okay. Now that's why I chose a specific guess 0, 0, and we'll see what happens. So now if we yes.
In the Jacobian you have there, shouldn't that be 5, 1, not -5?
Well, it's df1 by dx1, it's -5. So if you had defined it the other way around, it would still be okay. So you defined it as 5x1 minus x2 minus 2, right?
Yes.
Yeah, doesn't matter. The way I defined it here, df1 by dx1 is -5. And df1 by x2 is 1. You defined the negative of that.
Okay.
Yeah, but it doesn't matter because you've rescaled the entire matrix by a negative sign, so that doesn't matter. It doesn't affect the inverse of the matrix. Now, if you look at the solution, okay, with the Newton method, we get delta is minus J inverse times F, okay, and that gives you, delta x1 and delta x2 gives you the inverse of the matrix at times f1 and times f at x1 and f at x2, and then x1 and x2 you get the update. However, if you compare this with an initial guess of 0, 0, if you compare this to what you would have obtained from just solving the system of equations using a standard ax equal b method with initial guesses 0, 0. If you start with initial guesses 0, 0 for Newton's method, what you get, the solution that Newton's method gives you, is nothing more than A inverse B, okay? And that's shown on the right-hand side here in orange. In other words, delta, which is delta x1 and delta x2, is nothing more than minus J inverse, which is A inverse. So if you write this as AX equal B, your solution is X equal A inverse minus A inverse B. This is what you get over here, okay? And the negative sign will just adjust for, so actually there's a typo over here. This is 5 and minus 1, okay? So this is 5 and minus 1. Anyway, the point is when you, I will fix this before I post it. I'll fix the error, the typo here, and then I'll post it. The point is Newton's method with an initial guess 0, 0, and when you apply to a linear system of equations, you'll just get A inverse B. You just get the solution. And that's pretty cool, I think. Next, we can generalize Newton's method. I'm not going to hold you responsible for this, but the same strategy applies. And in practice, I would just use fsolve. However, in generalizing Newton's method, you can easily generalize it to n functions and n unknowns, or in other words, n nonlinear equations with n unknowns. And we call those x1, x2 to xn. And the residual functions would be f1 all the way to fn. Then your Jacobian matrix gets really annoying. Okay, the way I like to think about, I like to read the Jacobian matrix is row-wise. For the first row, you get all the derivatives of the first function with respect to all variables. So the first row over here, df1 by dx1, df1 by dx2, all the way to df1 by dxn. For the second row, derivatives of the second function, and so on and so forth. Okay, you fill in the Jacobian, and then the algorithm doesn't change because all we have to do is go back and rewrite our functions. So our Newton solver that we wrote will work for any number of nonlinear equations. You just have to define f and j correctly, okay? Because all it's doing is taking the inverse of j and multiplying it by f, or just solving the linear system of equations, okay? And the way we write this in general, like we wrote it for the single equation, is with xk plus 1 and xk as an iterator, okay? Again, that's kind of taking this one step further, okay? But know that if you know how to do it for 2 equations, you should know how to do it for 1,000 equations, okay? You just have to program f. Now, speaking of 1,000 equations, can you imagine programming the Jacobian for 1,000 equations? Especially if those equations are not, they're just like random, right? There's no like pattern in these equations where you could say, oh, the first entry here is this guy. You don't have like a recurrence formula for the Jacobian. It's really annoying. Okay, so now I have an activity for you. Can you suggest a way that we can calculate the Jacobian without having to do 1,000 by 1,000 entries with annoying derivatives? And this is a volunteer request. So just open up the microphone and talk, or I will pick you.
You could just use the finite differencing. Yes,
you could use the finite difference method. That's it. Just like we did with the one-dimensional case, all we have to do is do the derivative. The only challenge here is numerically compute the derivative with finite difference formula. You use forward or backward or central. You choose your little delta, which is the spacing, and then there you go, you got it. And that's one of the best ways to do it. Now, you have to be careful though here. You have to differentiate with respect to the correct variable. Okay, so if you have f of x, y, z, t, and whatever, you have to know what difference you're taking, okay, and what direction you're taking that difference. It's a little bit kind of beyond of what I want to cover over here, and I'm giving you the formula here. It's, you don't have to know that you can do a finite difference for the Jacobian in multiple dimensions, but you have to make sure what you're taking the finite difference for, which x, which unknown variable, right? In 1D, you just had x. You would do x plus h, f of x plus h minus f of x over h. Over here, you have f of xy. So you got to know, you got to take the derivative with respect to x and then respect to y, and then the second function with respect to x, respect to y. You have to know where you're adding that h to which variable. And with that, I will actually conclude nonlinear equations, nonlinear solvers,